Hello students, my name is Sumit Sagar Hota. I am a PMRA PhD scholar, IIT Palakkad. Today we will discuss lecture 51 to lecture 55 by Professor Ashok Sir, IIT Kanpur, of the subject Introduction to Airbreathing and Propulsion by NPTEL. This is the week 11 of the live discussion section. The prerequisite for this section is you have to go through lecture 51 to lecture 55 by Professor Ashok Sir of the subject Introduction to Airbreathing and Propulsion. In this section, first we will solve some of the MCQ questions, basic MCQ question for the rotary compressor, axial compressor, okay, and then we go to the problems of the axial compressor, okay. And if you specifically want to see the MCQ, the theory based questions for the axial compressor, you can see week 10 video which is uploaded in my YouTube channel, okay. Sumit Sagar Hota, okay, it is the channel name, okay. Let's quickly start the MCQ questions, okay. Rotary compressor are used where in quantities of gas are needed at relatively dash pressure, okay. This is the question, okay. The rotary compressor are used where large quantities of gas are needed at relatively what? At relatively low pressure, okay. This is what the uses of what? Rotary compressor, okay. Okay, next question. The rotary compression can be classified as dash, okay. Okay, so there is two types of rotary compressors are available. One is your displacement compressor, okay, and one more is your what? Steady flow compressor, okay. These are the two types of compressor available, okay. Okay, these are the two types of compressor. In steady flow compressor, compression occurs by what? Okay, if it is a steady flow compressor, okay, so how this compression will occur, okay. Okay, so steady flow in the question, what it's mentioned. Okay, in the what is mentioned in the question? Steady flow. Flow, what does flow means? Okay, flow means it's must having some velocity. Okay, okay, if there is velocity involved, then which kind of energy it will involve? Obviously what? Your kinetic energy. Okay, so what is this kinetic energy? It's not only the kinetic energy, it's the change in kinetic energy. Okay, okay, okay. So and how this kinetic energy is transmitted? Okay, it's through the rotor. Okay, so the answer of this question is A. Okay, in displacement compressor, compression occurs by what? Okay, okay, so displacement compressor. Okay, okay, so displacement, what does this displacement compressor means? Okay, always remember, if there is a question mentioned displacement compressor, it means that, okay, it based on which mechanism? Okay, it does not based on kinetic energy, it does not based on the potential energy. Okay, it's only based on the what? Trapping mechanism. Okay, why? Because it's having some what? Reducing space. Okay, okay, so air is compressed by trapping in the what? Reducing space. Okay, this is what the working or whatever things, whatever the mechanism of what? Your displacement compressor. Okay, okay. The rotary positive displacement machines are dash and compression is dash. Okay, okay, so the rotary positive displacement machine. Okay, displacement, you see, displacement is here. Displacement compressor, air is compressed by trapping. Okay, some trapping mechanism is there. Okay, in a reducing space. Okay, and steady flow compressor means it's transfer of kinetic energy through the rotor. Okay, That means now positive and rotary displacement both came into existence. Okay, so always remember displacement is positive. Okay, okay, the rotary positive machines are dash and compressor is dash. Okay, remember if there is a rotary and it's positive displacement is positive. Okay, okay, if displacement is positive, that means what it's going on. Okay, that means there is some what trapping is going on. Okay, or that means air is what compressed. Okay, air is compressing and there is some trapping is going on in the what cavity or the reducing space. Okay, if all these things are going on, okay, then what does it mean? Okay, that means the what, it cannot be what cooled one. Okay, it's a uncooled type. Okay, okay, uncooled means here we don't need any kind of cooling all this thing. Okay, further some other mechanisms are there for cooling. Okay, so it's an uncooled one. Okay, so the answer is uncooled, you now get to know. Okay, and always remember here most of the cases like rotary compression displacement machines, here we are assuming as the all are adiabatic conditions. Okay, isothermal nearly mostly not there. Okay, we are considering there is no heat transfer in this kind of system. Okay, so it's an uncooled as well as adiabatic. Okay, because if there is option cooled is there, okay, it's a very good question. If you don't know also anything, okay, positive displacement is there means, okay, positive displacement means what, either it can be cooled, because this cooled and isothermal are related. Okay, cooled isothermal related and uncooled and adiabatic are related. Okay, so if you don't know any of the option also, you can guess that it can be cooled or because cooling and isothermal are processes are related and uncooled and adiabatic are related. Okay, so that's the reason this can be, these two options can be the case. Okay, but for rotary compressor you should know, remember that if there is a positive displacement is there, okay, it's obviously what, uncooled. Okay, so positive displacement what, uncooled. Okay, positive displacement means what, uncooled. Okay, and compressor if it is uncooled, obviously it's a signal that obviously it's what, if there is no cooling, okay, how the process becomes isothermal. Okay, or why we need isothermal, there is no need of isothermal process. Okay, temperature remains constant process, why we need it? Okay, we don't need this kind of process. Okay, if there is uncooled one, so we need the adiabatic process. Okay, so uncooled and adiabatic are what, related for the positive displacement machine. Okay, you should know it's a rotary one also. Okay, okay, so the answer is D. Okay, the next question. The root blowers and vane type compressor are the types of dash. Okay, the roots blower and the vane type compressor are the types of dash. Displacement compressor, steady flow compressor, both of the mentioned and none of the mentioned. Okay. Root blower means what? And vane type compressor. Okay, there is two examples it's given. Okay, so displacement compressor, I show you what is the displacement compressor. Air is compressed by trapping it in a reducing space. Okay, you should know one thing. Okay, the name suggests everything. Okay, maybe roots blower you don't know. Okay, maybe you don't know, but this maybe you don't know. Okay, what is root blower you don't know. Okay, let it, because it's from the name we don't understand anything. Okay, vane vane type compressor. Okay, vane is mentioned. What does this vane means? Okay, vane means if there is some guide vanes, all these things are there. Okay, you remember always one thing, only in the cavity type of compressor, okay, these guide vanes are what there. Okay, so if you don't know also root blower what is the kind of compressor, if you know fan type compressor is a kind of what cavity kind of compressor where there is what some reducing space. Okay, if there is reducing space means what the gas can be trapped there. Okay, if there it is trapping mechanism there, that means what it is a displacement compressor. Okay, so answer is A. So displacement compressor types are root blower, also by the way this root blower also a kind of trapping kind of blower mechanism. Okay, which is also a displacement compressor. For a root blower, as a pressure is increased, the efficiency dash. Okay. Okay. Okay, for a root blower, as a pressure is increases, efficiency what decreases. Okay. So efficiency of root blower is inversely proportional to your pressure ratio. Okay. Okay. The band type compressor requires dash root blower. Okay. The band type compressor requires dash root blower. The answer is what? C. Okay. That means for the brain type kind of compressor, okay, we does not require any kind of more work input. Okay, with the less work input, it can work. Okay, so this is also one advantage of your what brain type compressor. Okay. Okay, sir. Let's go. Okay. The next question. Which of the following is the true for an axial flow compressor? Okay. Actually, all are true for the axial flow compressor because the blades are arranged in same manner as in reaction turbine. Flow of air is along the axis of compressor. Okay, I think this you everybody knows. Okay, flow of air is along the axis of compressor, that everybody knows. Okay, velocity of air changes when it passes through the blade. Okay, velocity of air changes. Obviously, velocity of air obviously change when it passes through the blades. That's for axial compressor. Okay, the blades are arranged in the same manner as in reaction turbine. Okay, so here the answer is what? D. These are all what? Working of axial flow compressor. Okay. For uncooled rotary compressor, the compression process is dash while ideal process is dash. Okay. For uncooled rotary compressor. Okay, uncooled and what? Rotary compressor. The compression process is your adiabatic. Okay. While the ideal process is what? Isentropic. Okay. One thing you can very well know is that, okay, if it is telling about ideal process, okay, ideal means always it will be what? Isentropic. Okay, because what is ideal means? It's a reversible one. Okay. Okay, and reversible, what is the reversible adiabatic called? Reversible adiabatic process is called isentropic. So, in which option the second part is isentropic? Here it's not there, here it's not there, here it's there, here it's not there. Okay, if you know only one part in this question, you can answer this question. Okay, no need of other also. But anyway, uncooled rotary compressor, the compressor process, if it is only asking about the compression process, obviously it will be what? Adiabatic. Okay, because it's not reversible, only normal, irreversible. Okay, the actual will be what? Irreversible adiabatic. Okay, so this is the answer of this, and this answer is your adiabatic. Or more precisely, if you write irreversible adiabatic. Okay. Okay. In an adiabatic irreversible process, the extra work is done to overcome friction. True or false? Okay. Adiabatic irreversible. Okay. Extra obviously, because you see, if it is a adiabatic and irreversible process is there, that means it requires more work to do the whatever done by reversible process. Okay. Okay, so in an adiabatic reverse irreversible process, the extra work is done to overcome what? Friction. So it's absolutely a what? True statement. Okay. 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 Now let's come to the problem. But an axial flow compressor of 50% reaction, blading has isentropic efficiency of 82%. It draws air at 17 degrees Celsius and the compresses in the pressure ratio of what? 4:1. The mean blade speed and the flow velocity are constant throughout the compressor. The inlet and the outlet angles of the blades are 15 degree and 45 degree respectively. From axial direction, blade speed 180 meter per second, work input factor 0.84, calculate flow velocity and the number of stages. Okay. Okay. Here in this question, it's not tell to do any kind of what? Velocity triangle. I am assuming that you know how to draw the velocity triangle, because in the previous class of the week 10 discussion I also saw. I think in the next question maybe I will discuss also the same. Okay. So let's quickly go through it directly. But you should see how to draw the velocity triangle of inlet and outlet, okay, of a axial flow compressor. Okay, that you can see in the my previous video. Okay, week 10. Okay, let's see what are the things given. Alpha 1 is equal to beta 2, beta 1 is equal to alpha 2. Okay, beta 1 equal to alpha 2 is equal to what? 45 degree given, and alpha 1 is equal to beta 2 is equal to 15 degree given. Okay, it's written that the mean blade, the inlet and the outlet angle, the inlet and the outlet angles of the blades are 15 and 45 degree respectively. Okay, get it? So inlet angle, outlet angle, everything given. Okay. So now let's go to the what are the other things given. Okay. What is U? 180 meter per second, where it's written blade speed. Okay, U equal to blade speed. What is your work input factor is represented by phi h, which is equal to 0.84. Okay. Okay. So what is the formula of U? U equal to VW1 plus VRW1 is equal to VF tan beta 1 plus BF tan alpha 1. Okay, I think better I should draw the triangle, otherwise it's very difficult for you to understand. Okay, okay, beta 1 alpha 1 beta 2 alpha 2 BF B2 this is your stator, this is your rotor, B1 BR1 BRW1 BW1 U BRW2 BW2 T U. Okay, what left? BR2. Okay, so that is the TS diagram. Okay, now what we have here? Okay, we have BW1 plus BRW1. What is BW1 plus BRW1? You see, equal to U. You can see from the velocity triangle left side. BW1 plus BRW1 equal to what? U. We just write down that same thing. Okay, if you see the left side triangle, okay, and you have to find out what? Tan beta 1. Then what will be the tan beta 1? It is BRW1 divided by what? VF. Okay, that means what is BRW1? BF into tan beta 1. Okay, similarly, what is BW1 from the left triangle right part? If you see, tan alpha 1 equal to BW1 divided by BF. Okay, that means what is BW1? BF into tan alpha 1. Okay, so now we can take common of VF. Okay, and it is VF into tan beta 1 plus tan alpha 1. Okay, now substitute whatever the value you have, okay, in the equation and find the unknown. Okay, we have u equal to 180 is equal to bf into tan 45 plus tan 15. Okay, if you solve, you get bf as 142 meter per second. Okay, and what is bf? Your flow velocity. Okay, now if we can calculate the work input per stage. Okay, okay, so what is work input per stage? Cp into delta ts is equal to phi h into u into Vw2 minus Vw1. Okay, so what is delta Ts? Equal to phi h into u into Vw2 minus Vw1. Okay, divided by what? Your Cp. Okay, so now you can calculate delta Ts. All the other things I think known. Substitute everything in the formula of delta Ts. Okay, what is phi h? 0.84 into what is u? 180. What is your Vw2? 142. Okay, it's all given in the what? Question, and whatever things not given we already found out. Okay, what is Vw1? Okay, if Vw1 it's there, Vw1 is I think not given. Okay, but we can find out that what is Vw1? Vw1 equal to Vf into tan beta 1, and Vf equal to what? 180. What is tan beta 1? Beta 1 is your 45 degree. Okay, so Vf into tan beta 1, if you do 180 into tan 45, if you do it, you get the value of your Vw1 as 38.05. Okay, get it? Okay, 1 divided by Cp or 1005. Okay, so what is your delta Ts now? Delta T will be your 15.64 Kelvin per stage. Okay, per stage, this is an important word you should remember. Okay, it's a function of staging in the what? Compressor. Okay, what is T2 dash? How you find out from this graph what is T2 dash? T2 dash will be your what? T1 into R to the power gamma minus 1 by gamma. Okay, and what is your R or Rp? More precisely, Rp is your pressure ratio. Okay, T2 equal to T1 into Rp to the power gamma minus 1 by gamma. Okay, T1 is your 290. What is Rp? 4. What is gamma? 1.4 minus 1? 0.4 divided by 1.4. What is the answer? 430.94. Okay, okay, now you what you get here? You get the T2 dash. But what is the T2? What is T2? The actual temperature. Okay, because in the question it's given the what? Isentropic efficiency. Okay. Okay. Here you see, here it's written isentropic efficiency. Okay. Of 82%. Okay. So T2 equal to T1 plus T2 dash minus T1 divided by isentropic efficiency. Okay. 290 plus 430.94 minus 290 divided by 0.82. Okay. So what is your T2? T2 equal to 461.88 Kelvin. Okay. Okay. So next question. So now total change in temperature across the compressor. What is the question asked? Is the flow velocity and number of stages. Okay. So flow velocity, I think all the flow velocity whatever it's there we found out. Okay. Now we are in a way to find out the what? BF will be your what? Flow velocity. Okay. This is the answer. Okay. The question it's asked the flow velocity. Okay. This is your answer of A1. Okay. And now we can find out the difference T2 minus T1. Total change in temperature across the compressor. Okay, equal to T2 minus T1. Okay, 461.88 T2. Here we see, here we find out for T2 461.88. Okay, T1, what is T1? 290. Okay, where 290 is given in the question 17 degrees Celsius. Okay, right? 17 plus 273 is what? 290 Kelvin. Okay, minus 290. Okay, if you do it, the answer you will get as 171.88 Kelvin. Okay, so what is the number of stages? Is equal to N is equal to 171.88 divided by 15.64. Okay, the answer is 10.9895, which is nearly equal to 11. This is your answer. Okay. Okay, now the next question. An axial flow compressor compresses air up to overall stagnation pressure of 10 bar with overall stagnation isentropic efficiency of 88%. The inlet stagnation pressure and the temperature are 1 bar and 300 Kelvin. The mean blade speed is 200 meter per second. The degree of reaction is 50% at the mean radius with air angles of 30 degree and 10 degree. At the rotor inlet and outlet with axial direction respectively. Okay, the work done factor is 0.88, the hub tip ratio is 0.4, the mass flow rate is 50 kg per second. The work out the following. Okay, what are the things we have to work out? Draw the inlet and outlet velocity triangle and show the compression process in TS diagram. Stagnation polytropic efficiency, number of stages, blade height in the first stage of the compressor. Okay, this is a very long question and we will solve it. Okay, so the first bit we will directly take from our previous question. This is your velocity triangle and your TS diagram. Okay, okay, this is the first question answer. Okay, okay, so you see what are the things given, everything we just see. Okay, what is isentropic efficiency? Isentropic efficiency is 88%. Okay, NC equal to 88%. What is U? U equal to (200 meter per second). R equal to 50%. The work done factor phi h equal to 0.88, d2 by d1 equal to 0.4, m equal to 50 kg per second. Okay, so here 50% reaction is there. Okay, beta 1 equal to what? Alpha 2 and beta 2 equal to alpha 1. Okay, So what are all the values given? Beta 1 equal to alpha 2 equal to what? 30 degree, you see. Here it's mentioned. The air angles are what? 30 degree and 10 degree. Okay. 30 degree and 10 degree means always remember. Okay. Yeah, first is inlet, then is outlet. Okay. 30 degree is the inlet and 10 degree is the what? Outlet. Beta 2 equal to alpha 1 equal to 10 degree. Okay. Apply the formula of T2 dash. Okay. Same formula we already applied. T2 dash is equal to T1 Rp to the power gamma minus 1 by gamma. Okay. What is T1? 300. What is Rp? 10. What is R? 0.4. What is, sorry, not R, gamma. What is gamma? Gamma minus 1. Gamma is what? 1.4 for what? Air. Okay. And divided by gamma is also 1.4. Okay. What is the value? Total value we will get T2 dash is equal to 579.2 Kelvin. So T2 equal to T1 plus T2 dash minus T1 divided by 0.88. Okay. What is T1? 300. T2 dash we now find out 579.2. Where is T1 written? You see, here it's written. The inlet stagnation pressure and temperature are 1 bar and 300 Kelvin. That means P1 and T1 given. Okay. Where pressure ratio is written? Where pressure ratio came? Where the pressure ratio written? You see. Here P1 is 1 bar. Okay. The axial compressor air up to overall stagnation pressure of 10 bar. Okay. So that means P2 is your what? 10 bar. Okay. So this is your P2. This is your P1. Okay. So P2 by P1 is what? So Rp is equal to P2 by P1 is equal to what? 10 by 1 is equal to 10. Okay. So same thing I put here directly Rp equal to 10. Okay. So T2 dash minus T1 dash. What is T2 dash? 579.2. What is T1? 300 divided by 0.88. Get it? Now solve it and get T2. What is T2? 617.27 Kelvin. This is your T2. Okay. So one thing you should note here is that stator means inlet. Okay. So if you see, this is, you can, other words you can write down, inlet velocity triangle, outlet velocity triangle. Okay, this is your TS diagram. Okay. Okay. So T2 now you get. Okay. So now here it's written the process is polytropic. Okay. Here it's written polytropic. Okay, isentropic efficiency 88%, it's given. Okay, and okay, you see in the question it's asked stagnation polytropic efficiency it asked. Okay, that means in the question if it is asking the polytropic process, what is the polytropic efficiency? So that means we can do one thing. It's nothing mentioned about polytropic, but if it is asking about the polytropic, then we have to convert the normal process, the ideal process, in terms of the polytropic process. Okay, so the same formula of T2 can be changed to polytropic by replacing gamma in place of what? N. N is your polytropic coefficient. Okay. Okay. For polytropic process 1 to 2, I change the pen because this is the new thing. Okay, other things we already done. Okay, this is the now from onwards we see the some new things. Okay. Okay, so T2 equal to T1 into Rp to the power n minus 1 by n. Okay, so T2 by T1 directly take 617.27 divided by 300 10 to the power n minus 1 by n. Take the logarithmic ln on both sides. Okay. So 1, if you solve it, 1 by n equal to 0.3136. So what is 1 by n? 0.6866. What is n? 1.4564. What is polytropic efficiency then? N by n minus 1 into gamma minus 1 by gamma 1.4564 divided by 0.4564 into 0.4 by 1.4 is equal to 0.9117 is equal to 91.17% efficiency. So work given per stage. MCP delta TS is equal to M phi H U VW2 minus VW1. Okay, so what is delta TS? We already found out. Delta TS similarly phi H into U into VW2 minus VW1 divided by Cp. Okay, so for that we need one thing. What is VW2 and what is VW1? Okay, if you don't know, then we have to find out first VW2 and VW1, then only you can put in this formula to find out delta TS. Okay, so first of all we know one thing, that what is Bf, the your axial velocity. You see, we already solved here. What is axial velocity? 180 divided by tan 45 plus tan 15. What is this 45 15? Beta 1 and beta 2. You see, so already we write down. If you see this formula, U equal to Vf into, if you see this one, okay, so U equal to Vf into tan beta 1 plus what? Tan alpha 1. Okay. Tan beta 1 plus tan alpha 1. Okay, so what is Vf then? U divided by tan beta 1 plus tan alpha 1. Yes or no? Okay, so that is what we are now going to do. So Vf equal to U divided by tan beta 1 plus tan alpha 1. So Vf equal to U divided by tan alpha 1 plus tan beta 1. Okay, is equal to, what is U? 200. Okay, it's given in the question. 200 blade speed is what? 200 meter per second. Okay, and alpha 1 beta 1 10 degree 30 degree already shown. Okay, tan 10 plus tan 30. If you solve, you get as 265.4 meter per second. Okay, your Bf. Okay, and if you know your Bf, you can find out VW1 and VW2 from the velocity triangle, and we know that VW1 equal to Vf into tan alpha 1. VW2 is equal to Vf into tan alpha 2. You can see from the triangle. VW1 equal to, from the left side triangle, VW1 equal to tan alpha in tan Vf into tan alpha 1, because tan alpha 1 equal to VW1 by Vf. So what? VW1 equal to Vf into tan alpha 1. VW2 from the right side triangle, you can see tan alpha 2. Tan alpha 2 equal to, what is tan alpha 2? Tan alpha 2 equal to VW2 divided by Vf. That means, what is the your VW2? VW2 equal to Vf into tan alpha 2. Okay. Substitute. Two 65.4 into tan 10, 265.4 into tan 30. Okay, 46.8 meter per second, 153.2 meter per second. You have everything, just substitute in delta TS and find out the answer. 0.88 into 200, 152.2 minus 46.8 divided by CP is here 1005. Okay. Delta T is 18.635 degrees Celsius. So what is the number of stages? Here is number of stages is equal to n is equal to T2 minus T1 divided by delta Ts. Okay, that is T2 minus T1, 617.3 minus 300 delta Ts, we now get 18.635. Okay, if you solve you will get n nearly as 17 stages. Okay. So blade height at the first stage they want to know. Okay, so number of stage is the second bit, third bit answer. The stagnation polytropic efficiency, here is that thing. Okay, 91.97. Second bit answer. Okay, what is the number of stages? 7. This is also your answer. This is your third bit answer. What is your blade height at the first stage? Okay. Okay. First stage means, okay, there will be what? First stage means 0, 1 and 1. Okay, because it's written first stage, not the second stage. Okay, so T1 is equal to, what is 3? What is your T1? Okay, T1 it's given. Okay, maybe you can write down it as Okay, so whatever we see as 1 as our what t01. Okay, or one way we can write down, I can write down it as okay, so t1 equal to t01. Okay, so then there will be a confusion, so to solve the confusion I will write down here or maybe I can represent it as t1 dash. Okay, so t1 dash is equal to t1 into t1 minus b1 square divided by 2 cp. Okay, so what is t1 given? 300 minus b1 dash is your what is b1 dash or whatever, sorry, b1 square. b1 square, if you do, what is b1 you should know first. Okay, and what is b1 is given okay, b1 is not given. Okay, so b1 we need to find out. Okay, how we find out b1? Okay, from the velocity triangle you know one thing, that if you find out sin alpha 1, sin alpha 1 is your what? bw1 divided by b1. Okay, so b1 is equal to bw1 divided by sin alpha 1. Okay, what is bw1? 46.8. what is sin alpha 1? sin 10. Okay, when you do this you will get 269.5 meter per second. Okay, what is t1? 300 minus 269.5 square 2 into 1005. If you solve it you will get t1 dash as 263.87. Okay, t1 dash divided by 1.4, p1 dash divided by 0.4 is equal to t1 by 1.4 P1 by 0.4. Okay, you see here T2 dash T and T2, and here T1 dash and T1 are different. Okay. Okay, you should note this thing. Okay, because here we are not, it's not a isentropic property T1 dash and P1 dash. Okay, here at the initial condition, okay, initial condition it's at the 300 and 1 bar. Okay, and after that whatever the condition it's there, okay, in the first stage, okay, that is the what, T1 dash. Okay, so you should note all these thing. Okay, don't confuse in this T2 dash and T1 dash. Okay, so now you solve for P1 dash equal to P1 into T1 by T1 dash by T1, okay, to the power 3.5. okay, this is 1.4 by 0.4 by 1.4. all this thing if you do 1.4 by 0.4, all this thing, then you get all this thing. Okay, and you find out P1 dash as 0.638 bar, 63.8 kilopascal. Get it? What is density? Rho 1 P1 by RT1, 63.8. Okay, so if you solve rho 1, okay, okay. If you know the density, that means you can find out the mass flow rate. Yes or no? So what is the mass flow rate formula? Rho 1 A1 BF, rho 1 dash A1 dash BF. Okay, mass flow rate I think given in the question, its mass flow rate is 50 kg per second. Okay, and half tip ratio is 0.4 given. What is half tip ratio? I will tell you. Uh, 50. Then what is density? 0.8424. Okay, 0.8424. What is A1 dash? Okay, A1 dash means, see here one thing you understand. One to two is the process. Okay, so there will be a what? And ratio, half tip ratio is there, half there, tip there. Okay, so that means there will be a change in what? This diameter. Okay, or more precisely if you tell height. Okay, there will be change in height. And how you represent it as maybe initial height is or d1, okay, because it's a circular cross section, one tip, okay, we take the cross section as circular, and we'll take d1 square is the initial one, and the change is d2 square, okay, into our bf. What is bf? 265.4. okay, so what is d1 square minus d2 square? 0.2848. okay, if you solve it, or you can just take the ratio of what? d1, okay, but in the question it's given half tip ratio, that is d2 by d1 is equal to 0.4. okay, so just to take the common of what? d1 square, 1 minus d2 by d1 whole square, that is what? 0.4 whole square. okay, so you can now calculate d1 as, if you just solve all this thing, take the square root, okay, 0.2848, 1 minus 0.4 square plus square root, okay. If you solve this, you will get d1 as 0.5827 meter. okay, now you have d1, okay, if you know d1, what is d2? d2 by d1 is 0.4. okay, what you have? d1 582.27 mm is equal to 0.4. so what is d2? 232.9. 232.9 mm. okay, if you know d2, what is h? Height of the blades. h is equal to d1 minus d2. okay, so what is d1? 582.27 minus 232.9. h is equal to 349.37 mm. I think this will be a third bit. okay, the blade height in the first stage of the compressor. okay, the last bit of the question, the fourth bit. okay, fourth bit is here. Number of stages. Where is number of stages? Yeah, number of stages is here. Then stagnation polytropic efficiency is here. okay, then is your plot is also here. okay, everything is here. okay, we solve all the questions. okay, now most probably all the type of question I covered of the axial flow compressor. okay, whatever the possible types of question can be asked in any kind of examination. Either it will be a mains exam, either it will be a MCQ exam, whatever the exams. Nearly every type I will ask, I will solve. Okay, and still if you have any kind of doubt, you can just ask me. Okay, and you can ask me all the doubts in the form of comments. Okay, in the my YouTube channel, Sumit Sagar Hota. Okay, all space is there in between my name. Okay, and that is also available. You can find my also YouTube site from the NPTEL. Okay, live interaction sections. Okay, and you can also ask any doubts in the question and answer forum of the NPTEL. Okay, and if there is any other problems, you can ask me regarding this lecture week 11. Okay, thank you very much for attending. Thank you very much if you are attending the recording of the video. Okay, good night. We'll meet next week 6 to 8. Okay, maybe we can have one summary section for 1 hour. Okay, we'll decide later. Okay, if we will I'll notify it, means NPTEL will notify it later. Okay, till then, happy learning and good night.